Great pleasure to be here. So I will talk about some joint work with Chong-Kum Lee from MIT and Poshakov from Carnegie Mellon. So the topic would be judicious partitions, and I hopefully will explain you what this means and show you that this is pretty interesting topic. So I'll start with a very classical problem both in combinatorics and computer science. So it's max-cut problem. So the idea in max-cut problem is you want to partition vertices of graph in two disjoint sets, A union B, to maximize number of crossing edges. So this is a very basic problem. I give you a graph. You want to split vertices into two parts so that to maximize the number of crossing edges. So this is a very classical problem. It's NP-hard, so we don't have any efficient algorithm for this problem. It's also NP-hard to approximate it pretty well, and the best approximation ratio which we have currently is the algorithm of Gomans-Williamson, which gives roughly a factor of 0.87. So I would be more interested in a combinatorial setting of this problem. So in a combinatorial setting, the history starts with a very classical fact, which I think you know, folklore, which says that every graph G with m edges has cut of size at least m over 2. So you can always guarantee, no matter which graph you take, a partition into parts which cross such that at least half of the edges crosses this graph. Okay? And the proof, let me briefly tell you the proof. The proof is very simple. Take random partition which means probability that vertex belongs to A equals probability that vertex belongs to B equals 1/2. So you split vertices into parts randomly, and then expected number of crossing edges would be, for every edge, the probability that it's crossing is precisely half. So it's either one vertex is in A and another is in B, or vice versa. So since probability for every edge is in half, by linearity of expectation, you get M over 2. And since expected number of crossing edges is N over 2, then you know that there is a cut of size. So this is a very basic statement. So now this question was extensively studied in combinatorics, and the idea here, which will also take this idea in this talk as a basic approach, you want to show some bounds on the number of maximum cut in various classes of cuts. So in particular, the first question which people ask, how tight is this bound? Can you get a little bit better cut in every graph G? And this was done by Edwards in 73. So what Edwards proved, that they exist always cut which does a little bit better than that, and actually the gain is roughly square root of m. So I'll write you some formula, and then I'll tell you why I'm so picky about writing all these numbers. So that's what he proved. So there exists always a cut of size n over 2 plus roughly square root m. And the reason why I'm writing this formula, because this is now tight. Okay? So this bound was not tight, this bound is tight for complete graph. So for complete graph, you cannot do better than that. If your graph G is a complete graph, with m edges, then you always achieve this. So now look on this error term. So this error term is really good when your m is quadratic in n, and this error term is linear in the number of vertices. Note that so far I didn't mention the number of vertices, but you can have your bounds both in terms of number of edges and number of vertices. So because for small values of m, this is not a really, square root of m is not really big number, there is another very interesting result, which was proved by Erdős, Gyarfas, and Hayakawa, which gives a different error term. So what they showed is that if G has no isolated vertices, then there is a cut of size at least m over 2 plus n over 6. So for the duration of this talk, always m would be the number of edges in my graph, and n would be the number of vertices. So you can always get at least x n over 6 in the cut bound. And again, this is type. So if you take a disjoint union of triangles, then you see that on this graph, the largest cut you can get is precisely 2/3 edges, which is exactly m over 2 plus n over 6. So there are many more results of this sort. There are lots of people who worked on this problem, including Nora Alon, who is here, Bela Bolobash, Michael Krivarevich, Alex Scott, Shearer, and so on. So what they did, they took various classes of graphs and obtained various such estimates, and many times they managed to obtain a tight estimate, knowing what is the best bound you can get from max cuttings. But this is not the avenue we are going to take in this talk. Instead, let me go back to this random partition algorithm. So you remember, so the way to get a big cut in the graph is just to split vertices randomly. Now if you split in vertices randomly, note the following thing. That in this random partition, if I split it into parts A and B, expected number of edges in A and expected number of edges is m over 4. So we not only expect a lot of edges across, we also expect few edges in every part. So one major question which you can ask, can you guarantee me this scenario in every graph? Can you split every graph so that there are few edges in every part? Obviously, this immediately will imply that you have a large part. Now note that here you already have a problem because linearity of expectation works very well when you try and optimize one parameter. When you're trying to optimize two parameters simultaneously, you cannot use linearity of expectation. I mean, you can say that expectation here is m over 4 and m over 4, but it will not imply you that you can guarantee these two quantities happen simultaneously. You need now to know something about probability. The average is already not enough. So this is indeed was question of Erdős, and Erdős conjectured that they exist always. They exist partition A union B of G with at most m over 4 plus big constant square root of m edges in A of B. So Erdős conjectured that nevertheless you can guarantee such a scenario in every graph. You can split it into vertices into parts such that there are at most square root m over 4 plus some error term. Now note that this error term is needed. So you cannot guarantee me also the expectation give you precisely m over 4. You can never achieve this thing. And the example is if you take G, a complete graph of 2t plus 1 vertices, and so no matter how you split it, so if you think what would be the best way to split it, is to have t vertices here and t plus 1 vertices here, and the number of edges in this part, in the t plus 1 part, is t plus 1 choose 2, which would be, if your m, the number of total edges, 2t plus 1 choose 2, is precisely equals m plus some constant square root. So you really have to have by square root more, m over 4. So for complete graph shows that square root everything. So the conjecture of Erdős was solved by Bolobash and Scott, and actually in very strong sense. So what Bolobash and Scott showed that every graph G has cut A union B such that number of crossing edges is m over 2 plus square root of precisely the best bound which we had, m over a, and so on. And number of edges in A or B is at most, so this is at least, is at most m over 4 plus square root of m over 32 and some error terms. And they know precisely, so there are some, I will spare you writing all these numbers. There's some constant error terms here, and this result is again tight for complete graph. So they basically, not only they confirm Erdős conjecture, but they completely understand what the best results you can have. Now, what they suggested after they proved this result, it basically said that, look, this is a really very interesting direction, which they call judicious partitions of graph. And the general topic of judicious partition deals precisely with the equations where you're trying to find certain subgraphs or certain partitions in your graph which optimize several parameters simultaneously. Okay, so instead of usual setting where you're trying to optimize one parameter, here you're trying to optimize several parameters simultaneously. And let me right here. So examples which you can think of such equations is k-cut. So k-cut means you split vertices instead of 2 parts into 3, 4 parts, and then you can say, I want at least that many edges between first part and second, at least that many edges between third and fourth, and so on. Or you can think about bisections. I will in a second give you the definition. This will be one topic I will mention. Digraphs, not necessarily working with graphs, or working these equations in hypergraphs. So there are many open equations in this area, and as I said, the main difficulty is that once you have 2 parameters, you can compute averages. They don't tell you anything because you cannot guarantee sometimes these 2 averages to happen simultaneously. Any questions so far? So this is the direction I'm going to go to. So I want to talk about judicious partitions in graphs. So I will describe you several fundamental problems in this area, and I'll tell you some new results about these problems. So the first thing which I said I want to talk about is bisection. So bisection is very natural parameter. It's exactly like max cut. So I want to split graph into 2 parts to maximize the number of edges across, but I also insist that this splitting would be fair. Half vertices on one side and half vertices on the other side. So bisection, it's a partition of vertices A union B of graph such that both A and B are of size n over 2, such that number of crossing edges is maximized. So this is a bisection. So again, it's NP-hard parameter, so we would be interested in various combinatorial statements, saying that what kind of bisection we can guarantee in every graph. So now if you look on this random algorithm, which I described, so random algorithm says for every vertex to find a big cut, toss a coin with probability half put it left, with probability half put it right, you get a large cut. You can adjust easily this algorithm to give you a large bisection. Instead of choosing every vertex probability half left and right, then you cannot control that the parts will be of size n over 2, you will have deviation. What you can do is you can pick a random set A of size n over 2 and take B its complement. And then if you analyze it, again, it's very easy to compute the average, you get half of the edges across. So it's very easy to get a bisection. So pick a random set of size half, and B is its complement. Again, for every edge, it's very easy to compute that with probability half it's going across. It's actually a little bit better than half here now, even improving, and you get a bisection of size half of the edges. Now I want to ask this question. Okay, so I can have a large bisection. Can I have a bisection which, in addition to having many edges across, have very few edges in every part, okay, in both parts A and B? So this is the question. And this was the question of Bolobash and Scott. Is there bisection with roughly m over 4 edges in A and B? Yes, obviously such bisection will have many edges across, but my goal is to have few edges inside A and few edges inside B. Okay. Now if you think a minute about this problem, you realize that unfortunately the statement is no longer true. There is a very simple counterexample. Okay. So take a star. Okay. With vertex B inside. So no matter how you partition this set, this graph into two sets, if you look, yes, so here is your A, here is your B, and imagine your vertex V is inside, you need to put V somewhere. So if you put V inside A, then there would be lots of edges inside A, many edges across, and no edges inside B. So basically all your m over 2 edges will fall inside A. So you will not be able to guarantee me m over 4. So Bolobash and Scott thought a little bit about this problem, and they proposed several interesting ways how to fix it. Now if you think a little bit, you'll see this is pretty natural and obvious ways. So let's look on the counterexample. So what we have in the counterexample, which is kind of pretty jumping out. So first of all, we have a vertex of very large degree, of degree m. So one thing we can do, we can say, okay, let's take a graph where there are no vertices of linear degree. That would be one option. Another option, we have many vertices with degree 1. So another thing we can say, okay, let's assume that minimal degree, or the total number of edges, is large. And this would be two ways to fix it. And indeed, Bolobash and Scott make a conjecture saying that if max degree is little of m, so you don't have very large degrees, or, so this is Bolobash and Scott, or mean degree goes to infinity, then there exists bisection with roughly m over 4 edges in both parts. So this was the first conjecture which I mentioned. And then they went further. So they said, okay, I'm assuming minimum degree much bigger than 1. So actually, it's very interesting to ask what happens already if the minimal degree is 2. So of course, if minimal degree is 1, I cannot gain anything. There is a graph where in one part would be half of the edges if I take a bisection. Okay? Can I go below this half if I increase the minimum degree to 2? And indeed, they conjectured that the answer is yes. So they said if delta, which is mean degree, in the graph is at least 2, then you can have, there is bisection with at most m over 3 edges per part. So you can go, you cannot achieve maybe m over 4, but you can go below m over 2, which is this example. And moreover, they ask what happens for larger. So one set of results which I want to report is that we have a solutions to all these questions. And I think it's pretty interesting solution. So it's combined some combinatorial ideas together with probabilistic arguments. We already saw that they should be very handy in this problem. The theorem, which we prove together with Chongbum, Lee, and Boschen law, is the following. So first of all, indeed, one or two, like here, imply. So if you have either no high degrees or you have many edges, they exist bisection with less or equal 1/4 plus little o 1 m edges per part. And this is actually not very difficult. I think they just maybe simply overlooked, or maybe they didn't believe that there is a simple solution. So I'll briefly sketch you the solution. It uses a second moment argument. It's not very complicated. So actually the second statement is more complicated. So before I'll tell you our second statement, which gives this, in particular it proves the conjecture 2, and it gives much more general statement from which conjecture 2 is a special case. So we know the answer what should be the best bound for how many edges you will have in every part for every delta. So let me give you the examples, and then I'll mention the theorem. So let me first show you the example which shows that for graphs with degree, minimal degree 2, there are graphs, so no matter which bisection you take, you will have one part with at least m/3 edges. Here is a graph. It's actually a very simple graph. It's a bucket of triangles. So note that this graph has 3/2 n edges, right? Because it has n/2 triangles. And on the other hand, part with V will have n/2 edges. So if you, no matter, again, it's the same story, no matter how you split it, you need to put V somewhere. And this part has n/2 vertices, and V was adjacent to everybody. So this part will have n/2 edges. So it's exactly 1/3 from the total.
K3n minus.
That's true. So I'll talk about it. So there is another example here, and that's what makes this conjecture a bit more difficult to handle. That this example is not unique. Typically in combinatorics, especially in extremal problems when you're trying to minimize something, it's very handy if the example is unique, then basically you can kind of have certain procedure which converges to this example. So here this is not the case. There are other examples. But let me first give you a general setting. So what would be for general delta? So how I will construct a graph for general delta. So let's assume my delta is even for a second. Actually, interesting thing happens when you look on odd delta. So again, I take vertex V. Vertex V would be adjacent to everything. So this is a neighborhood of V. And then inside the neighborhood of V, I put cliques of size delta. So for general delta, the example will look like that. So if you look on this, it was vertex adjacent to everything, and I here put K2, just edges. So for general even delta, I just put here cliques of size delta. And then the bound which you get, then for every bisection, there is part with the same argument shows there is a part with delta plus 2 divided by 4 delta plus 1. So that's asymptotically the other small delta. If delta is 2, this gives you third. If delta is 3, you can have 5 over 16, and so on. And now note that it's also kind of with a good correspondence to the first theorem, because when delta tends to infinity, this converges to 1. Okay? So what we proved that that's always achievable. So not only in this example, but if you give me any graph with m edges, there is a bisection such that such that both parts have at most that many edges. And as Noga pointed out, the problem a little bit with proving such a result is that it has more examples than that. So that was a very pretty example, and you would be happy if this would be the only example. But there is another example which roughly does exactly the same for you. And this example, another example, which achieves roughly the same quantity is to take a complete bipartite graph, delta plus 1 here, and n minus delta minus 1 here. And it shows you exactly the same thing. Let's analyze it for a second. Let's take maybe, so you understood the example, so let me change it. Let me take specific delta equals 2, just to show you that it also gives you 1/3. So if you put here delta equals 2, then you will have here 3, and you have here roughly n minus 3. And now, no matter how you partition this graph into 2 parts, yes? So let's call it x and y. So for every partition A union B, there is part which has 2 vertices from x. Okay. And these 2 vertices we take, so all these vertices are connected to everything. So again, it's bisection, so this part has n over 2 vertices. So these 2 vertices from x contribute you roughly twice n over 2, which is n edges in this part. And total number of edges is roughly 3n. So again, it's 1/3. But you see, it's a very different, in a spirit, example compared to what we have, which shows you that certain type arguments which you would want to do for this problem will not work. So any questions? So this is first result which we get. And as I said, so this is an example of what kind of equations you can ask about bisection. Now let me move to the second bullet which I mentioned there, actually diagrams. So now let's talk about diagrams. So what is a diagram? So you have a graph, and you just have a directions on the edges. So that's all. By the way, I allow anti-parallel edges, so you can have the digraph definition. Just graph these directions. Actually, this thing, for example, allow. So I'm looking on a very general class of digraphs. So I'd not allow you multiple edges, but for example, edges between 2 points pointing in different directions are okay. Now you can ask, so what would be the most basic kind of partition problem for directed graphs? So again, you can ask, okay, can I partition vertices of directed graph in 2 parts to have many edges between them? Now if you do this argument, which I deleted, but if you take a random partition, okay, so note, random partition of any graph G, or maybe let's, for directed graph, let's just use letter D of A union T for the word directed, has number of edges from A to B, and over 4. So if you take any diagram with n edges and you take a random partition half and half, the same analysis which we did so far guarantees you at least quarter edges from A to B. Just because now the edge has a direction, so now the probability that it goes from A to B is not half but quarter, because you need first vertex in A and first vertex in B. The other direction doesn't work. Okay? So we know, okay, cool, we can guarantee quarter edges from A to B. We can, by the same token, we can guarantee quarter edges from B to A. So the most basic question one could imagine in this area is, can we guarantee both? Can we guarantee for any directed graph a partition which has many edges from A to B and also many edges from B to A? And that was a question which was posed by Alex Scott. Question. Can we have D equals A union B with many edges from A to B and from B to A? Okay. So that's the set. I want a partition of digraph which gives me many edges in both directions. Now again, if you think a little bit and you already remember the example which I showed you, you should be suspicious. You should try very simple graph. And the most basic simple graph you can imagine is again star, which I don't direct in an inappropriate way. So take a vertex V and orient, let's say, all the edges towards V. Take a star. And it will show you that the answer is no. Yes, for the same reason, because you know, if this is your partition A, B, and here is V, you will have only edges from B to A. You will not have edges. So what Alex suggested, because they already with Bolobach had a similar conjecture for bisection, is there is a very simple way of fixing this problem. And what would be the simple way? So the simple way would be just to guarantee that the minimal out degree of your graph is a bit bigger than 1. So note that in this question, the minimal out degree in my graph was 1. Actually, I'm cheating. It was 0 because V had no out degree. But note that V plays no special role. Instead of V, I could put here cyclic triangle. So to guarantee that every vertex has now out degree 1, and the answer still would be roughly the same. Because the small gadget which I will put instead of V will make no difference. So basically, I only care about the out degree of majority vertices, which is here 1. So the question, given D digraph with minimal out degree delta, is there C delta such that there is a cut with C delta M edges. Let me, for simplicity, from now on write this, which means I want C delta M edges both directions, from left to right and from right. So first of all, before I'll tell you what we know about this question, so let me give you some examples, which at least give you some bounds, or at least show you some construction and indicate what is impossible. So examples. So let me start with delta equals 2. So look on the following thing. So take a vertex V, orient everything to vertex V, towards the vertex V. And inside the rest of the vertices, so everything is oriented towards V, take cyclic triangles. Maybe let me draw it bigger. Okay. So again, you see that the V has the out degree 0, but as I said, I can easily fix this V by putting some small gadget there. V plays no special role. So if this is your digraph, then you can do the computation and see that, no matter how you partition it into two parts, the part in which V is located, there would be much more edges. Yes, so if this is my partition, and here is a V, so there would be much more edges that direction than the other direction. Okay, so here would be only few edges. And the reason why it would be few edges, because the only way you can get edges are from the cyclic triangles, and every time you put cyclic triangle, it should go across, and also it has two edges across, only one you will get in the direction you want. So the number of edges which will go across would be only one from every cyclic triangle. So total, n over 3, which is m over 6 edges. So this example shows you that there is a digraph without degree 2, such that no matter how you split it into parts in this cut, there would be a direction where only at most 6, not quarter, but 1 over 6 edges were. And now you can do a similar example for larger delta. So for example, take delta equals 3, then you can do the same thing. You can take vertex V. You take here, all guys are points towards V. And inside these vertices, you take K5 with a Eulerian So now split your vertices into n over 5 clicks of size 5, and every click of size 5, it's a subgraph which inside has degree 4, so oriented in such a way that out degree and in degree of every vertex is 2. So you can orient every such gadget in such a way that out degree and in degree of every vertex is 2. And if you do the computation again, the same computation, the only edges, if you put V on the left, the only edges which you can have from left to right are the edges which come from these clicks. But these clicks, because of Eulerian orientation, when they cut this cut, there are exactly half of these edges which will go from left to right, and half of the edges will go from right to left, and you're losing on this. So for this thing, you will get a constant. So C3 So this example showed that for minimal degree 2, you cannot expect more than 1 over 6 edges. So for minimal degree 3, you will not expect from more than 1 over 5 edges. Okay? So this will show. And what we believe is that you can continue this example for every delta, and that would be an answer for the problem of Alex Scott. Yes. So we believe that the answer is yes, there is always such C delta, and actually C delta is given by this example. Again, asymptotically, because there are might be more examples than what we're pointing out. And so the theorem which we know to prove, so we not only have a conjecture, but we have a little bit more reason to believe that this conjecture is true, is the theorem that C2 is indeed 1,6, and C3 is indeed 1,5. So we know to prove these first two cases of our conjecture. We know to prove that indeed, again, now the statement means for every digraph with n edges, with minimal out degree 2, there is a partition such that at least 1 over the 6 edges go in each direction. If the minimal degree is 3, then at least 1/5 of the edges go in each direction. And then you can continue and get that when your delta is going, you're getting closer and closer to 4. Actually, again, using second moment method, which I might sketch now, it's not difficult to show that when minimal degree is really large, you indeed will get quarter in every direction. So, let me say ideas of proofs. So as I said, the proof kind of uses this basic approach of random partition, but random partition can guarantee only by averaging only one quantity, so we need to guarantee two quantities. So we do a second moment, so we want to say something about probability. And surprisingly here, the second moment is very easy to analyze. Okay, so D is digraph with m edges. Okay, partition V in A with probability 1/2. V belongs to B with probability 1/2. And now let's look on the number of edges across. So let's, X would be the number of edges from A, edges from A to B. Now note that my X is a sum of indicator random variable over all edges of D, where XE is just 1 if E was from A to B, and 0 otherwise. So now I know already that expected number of X is exactly m over 4. Yes, for every edge, if this is my edge, UV, then what is the probability that it's across? With probability half, this is in A. With probability half, this is in B. So the probability that these both events happen is a quarter. So by linearity of expectation. But now I want to claim the same thing. Oh, let's also have Y to be the number of edges from B to A. Yes? I want to do the same for a random variable Y, and then I want to claim something about both of them. So I want to have something about probability that X deviates from its expectation by certain quantity. So I need a second moment. So let's compute the variance of X. And now note that when you're computing the variance of X, so the main contribution will come from the covariances. It's very easy to see. So it's a sum of covariances of XE and XE prime, where E and E prime are some edges. And now the nice thing about covariances is that there are lots of pairs for which this covariance is 0. So if you take, basically the only contribution to covariance which can happen is if you have two edges, E and E prime, which sharing the same vertex from which they eliminating. So this one pair which will give you something to covariance. And what it will give you to covariance, it's a constant. It's roughly 1/8 minus 1 over 16, which is 1 over 16. And the reason is the following. What is, so you remember, covariance, that's expectation of XE equals 1 and XE prime equals 1. So the probability that all this, both of these edges are going across is 1/2 that this vertex is in A, and 1/2 that this vertex is in B, and 1/2 that this vertex is in B is 1/8. But if you multiply 1/4 times 1/4 is 1 over 16, so that's why you're getting this. Or there is a similar scenario when they both pointing in the same direction. And everything else gives you 0, or actually even negative covariance. If you know you have two edges, one from the vertex, one's coming from the vertex and one entering the vertex, you get a negative covariance. But the bottom line here is that the covariance is less or equal than sum of the degrees of the vertices squared. It's because note that we precisely counting, for every vertex we just counting pairs of edges which touch it. And sum of the degrees of vertices squared is at most, so substitute instead of one of the dB a maximal degree, and then the rest would be sum of the degrees, which is a number of edges. And now look what you can say. So, by the way, the same argument applies to the bisections. You're getting for the same price a proof of Golubosh and Scott conjecture for the bisection. So from here you know that your expectation is m over 4.
For the bisection, it's not exactly zero, right? Almost zero.
Yes. That's true. So the expectation is m over 4. The variance is this. So if variance is much smaller than m squared, you can have a probability of deviation much smaller than, let's say, half, and therefore you will guarantee me that both the number of edges from left to right and from right to left are okay. And what does it mean? So now you see, so the maximal degree in your directed graph is at most 2n. So it has n vertices, so at most 2n. So therefore it immediately implies that, for example, if the number of edges is large, then you have everything. So now a few more words. Okay, so this will take care, this type of argument, you will actually get not only 1/6 of the edges in each direction, or 1/5, you actually get into quarter. This takes care, yes, so let me write. Since delta is at most 2n, if n is bigger than n, we're done. So now what happens if I have few edges? Remember, my extremal graphs have very few edges. It has 2n edges. So now you need to analyze your construction a little bit more carefully. So basically what we do is we start by the vertices of large degree. So take the vertices of large degree first, exactly like in this example. So what I will do, I first do something with the vertices of type V, which has lots of edges coming to it. And I split this into two parts, and I maybe put few vertices here and few vertices here. Not necessarily my situation is like this. It's not necessarily, nobody guarantee me that there is a vertex of, one vertex of large degree. But I do this splitting not randomly, but deterministically choosing the best splitting. So you start with the vertices of large degree, you split them into two parts in such a way that to balance as much as possible edges from left to right and edges from right to left. So suppose these are some edges going on. So vertices of large degree are split nicely. Now what happens here, so here the degree is low. So random partition works. So because in the what's left the degrees are low, random partition will work. The problem is that you not always would be able to split the vertices of large degree so that exactly half of the edges touching them going from left to right and half going from right to left. Exactly like in this example. Whenever you put V somewhere, this side gets a big advantage. You need now to compensate in getting edges from V's here from A to B. So I actually, now m over 4 is not a good deal for me. So also the random works here, having quarter of the edges each direction is not good for me. I want a little bit more. And apparently you can achieve something a little bit more. And let me just give you the example of something you can prove, which is exactly in the spirit of the thing, which we did, by the way, for bisection. So if you remember, so what you want to do here is to take a random bisection, split half of the edges. I'll be done in 1 minute. Half of the edges to the left, half of the edges to the right, so that you know you already use this good partition for vertices of large degree, but you also want to have a little bit more edges, let's say, from left to right. So, for example, the theorem which you can prove is a variant of Erdős, Gyárfás, and Kohayakawa result for bisection, which you can apply here. So you remember Erdős, Gyárfás, and Kohayakawa said there is always a cut of size half of the edges plus n over 6. So you can ask, can you get a bisection? Suppose I want half and half, and I want more edges from in this bisection. So the answer is yes. They exist So you need to put an additional restriction. So you remember when I was talking about this problem, I always said that having a star is an issue. So if you tell me that you don't have in your graph large stars, which would be scenario here or scenario for bisection, then you can have a bisection of size half of the edges plus n over 6. Or you can have a directed cut half and half with quarter of the edges plus some linear term going in the direction which you want, which will allow you to fix this lack of edges in one of the direction, and that's basically the idea.
Any questions, comments?
Try to minimize the chromatic numbers of the parts. So find the partition which minimizes the chromatic numbers of the parts.
So you see, chromatic number some kind of additive thing. Yeah? Like if you give me a graph with chromatic number 10, then I can look on the coloring. So I can take 5 color classes on one side and 5 color classes on another side, and then I would be guaranteed that both sides have a chromatic number 5. Now, a probably more interesting question would be, suppose I put certain restriction on the size of the classes. Yes, suppose I'll tell you, look, I want to take half of the vertices to the left and half of the vertices to the right. Unfortunately, then you will not have a really interesting, I mean, it's an interesting result, but they're known and they're very negative. So you can have graphs with very large chromatic number, but maybe if you take aside some part of it, no, actually not. I think it's always.
You can always make it.
It's always. You can always make it
half
half
the square root. That was his exercise.
Yeah, half of the square. Yes. You can always make it roughly half of the chromatic number plus a little bit, even if you insist on half of the vertices. Just you're doing it right. Yeah, that's true.
So you said this conjecture for the directed thing, and then you get pretty close to it, or for general C delta?
For general C delta, we don't have. I mean, you get pretty close from just random partition, especially if your delta is large. But so here it would be interesting to get it precise because it's nice.
It looks like for every fixed delta, it's more or less a finite problem because you just have to look at the big degree.
It's very difficult.
It's a big finite.
Big fine problem and things deteriorate because you need also do correction here, and the correction kind of also complicates. Yes, you're right. So it looks like maybe you would be able to do it. So for bisection, we managed to do it because it's a very similar approaches, but the kind of the problem, the computational problem you get with high degrees, getting extremely more complicated. Or at least for directed graphs, we didn't see the way to do it in a nice way. For bisection, we found some. It still uses linear programming. You need to write certain inequalities. It's a lot of work. But here we just don't see it.
Huh? One more question. Could you make the effect as a construction, the randomize or something?
I see, effective. So, some of the results, yes, we can randomize it because what we're using certain large, so I didn't show you the proof, but we're using, so second moment, obviously you can randomize it, that's not a problem.
What about the high degree?
The high degrees is deterministic completely, so it's not even,
It's hard.
why?
It's hard. How would this be
No, but you see, but I'm not finding the best bisection, yes? I'm just finding, no. So it's very difficult, given a graph, to find an optimal bisection. But I'm so far saying that every graph with certain number of edges has large bisection, which may be very far from optimal. Maybe the optimal is that you can have all the edges in the graph.
I see, but the numbers.
No, the numbers which we getting, we can get effectively.
Any more questions? Okay, let us then the speaker once again.